So far we had balanced the chromiums by putting a 2 here. Then we balanced the oxygen by adding the 7 water molecules. 7 waters have 7 oxygens. That equals these 7 oxygens. And then part C, I did the 14 hydrogens to balance out those 14 hydrogens. And we had just gotten to the part where we're trying to figure out how many electrons to add. So that part we have to look at. We have a -2 charge for the dichromate and 14 +1 charges. So the reactants combine together for +12. The products, well, there's 2 +3s and the water is a 0, so that's +6. And we had said if we added 6 electrons over here, those 6 electrons would drop the charge so that it also equaled +6. And that's our goal, is to get both sides of this half reaction to have the same charge. +6 charge when I add the electrons, the dichromate, and the hydrogen, and then on the product side, +6 charge with the chromium and the water. Let's try that again, but with the other half of the reaction. We have water with no charge, and then nitrogen monoxide with no charge. On the product side, we have 4 positives, and we have this nitrate. So that's +4 plus a -1, so that equals +3. Or again, on this side, we had 0 plus 0 equals 0. So I have to add electrons to drop this charge down. I need to add 3 electrons. If I add 3 electrons, I'll get a combined charge of 0 for my products as well. So the 0 charge now equals the 0 charge. So we've done steps A, B, C, and D to both half reactions. We balanced the elements, we balanced the oxygen, we balanced the hydrogen, then we balanced the electrons, or we balanced the charge using electrons. Now we have to make sure that the electrons are equal in both reactions. So here we have 6 electrons, but here we only have 3. So we have to multiply this reaction by 2 to fix those electrons. That's 6 electrons, 2 nitrates, 8 hydrogens, 2 nitrogen monoxides, and then 4 waters. And here's what we get when we combine it all together. The dichromate, the hydrogens, the waters, the nitrogen monoxide, those 6 electrons, 2 chromiums, 7 waters, 8 hydrogens, 2 times 4 is 8, 2 nitrates, 2 times 1, and then 3 times 2 is our 6 electrons. Then we have to cancel anything that's identical on both sides. So let's find the identical species. Here's water. Here's water. So 4 waters and 7 waters. So we're going to cancel out, these 4 will cancel out 4 of those, leave us with 3. Here's hydrogen. Here's hydrogen. Some of these will cancel out those. And then all of the electrons cancel out. And they always need to cancel out all of the electrons. And when we combine it together, it simplifies down to just this. Dichromate, 6 hydrogens, 2 waters, 2 chromiums, 6 waters, and 2 nitrates. That's a long process for one problem. It takes a while to get used to it. I strongly suggest you practice some of these either in your book where the answers are in the back so you can get a lot of practice, or we have some homework problems we also need to work on. These take a bit of time until you get used to it. And you have to go in slow motion, otherwise you'll make a major mistake as you're going through it. Also, you have to take into consideration, am I working in an acidic solution or am I working in a basic solution? Now, this reaction was balanced assuming an acidic solution, and that's why we have 6 H pluses here. So it's reacting in an acidic environment. But if we needed to balance it in a basic environment, there's really only one extra step. And that extra step is to look at the reaction and say, if I want to balance this with base, I'm going to add hydroxide. 6 hydrogens plus 6 hydroxides would give me 6 waters. But if I add 6 hydrogens here, I'm also supposed to add it on the product side. So these 6 here are now 6 waters. But like in the previous example, we have a common species on both sides, and we need to reduce it down. So these 3 waters will knock out all but 3 of those waters. Now it's balanced as if it was in a basic solution. So we have the chromate, the dichromate, plus the nitrogen monoxide, plus 3 waters produces everything, and at the end we'd have those 6 hydroxides in the basic solution. And on top of that, we're going to be using these balanced equations in conjunction with stoichiometry. So in this example here, we have potassium permanganate as an oxidizing agent, and it is titrated with some calcium oxalate. So it's potassium permanganate plus calcium oxalate. And then the ionic form of the equation is given below. So here's the permanganate and the oxalate, and it must be that the potassium and calcium are just spectator ions. So they're being removed, and that's where they've been. That's where they've gone, if you're wondering that. The spectator ions have been removed. So the first thing is to balance this reaction. So we took this and split it apart. 1 Mn, 1 Mn, 4 oxygens, so I did 4 water molecules, 8 hydrogens, so 8 hydrogens, and then those electrons added up on each side, and I saw that I needed 5 electrons to balance out the charge here with the charge over here. And then the oxalate, all I had to do for that was multiply the carbon dioxide by 2, and then add 2 electrons. And then the least common multiple of the electrons here, had me multiply both by these, and then I put them back together. So here they are, put back together. And the reason I had to do this, so I could get the mole ratio here in the stoichiometry of this question. And the stoichiometry of this question is 30 milliliters of the MnO4 was required to reach the end point. So 30 milliliters, and the MnO4's molarity is right there. So milliliters converted to liters. Here's the molarity, give me moles. And I'm trying to calculate how much of the calcium oxalate was there. So I did the mole ratio from permanganate to oxalate. So permanganate to oxalate, and every oxalate would come from calcium oxalate. So that's a 1-to-1 ratio. Some people skip this step here. That's fine, since it's just a 1-to-1 ratio. And then 1 mole of calcium oxalate would be 128 grams. That's the molar mass. So we've calculated the mass of the oxalate that was in that impure sample. So this 0.468 grams of calcium oxalate in the sample. And then we went a step further to figure out what the purity of it was. We divided the mass by the sample's mass. We see that it's a 56.2% calcium oxalate. We have a little follow-up question that's not too hard. How would this reaction balance differently in KOH? Well, that would be basic. And so the mole ratio would stay the same. It's just that we'd have to have enough hydroxide to cancel out all this acid. It would make a lot of water, and we'd have to simplify it down. So we're going to be balancing these new oxidation reduction reactions and doing stoichiometry with them. It's really vital that you get good at balancing oxidation reduction reactions, working your way through these steps very carefully. It takes practice, it takes precision, and good luck.